In this video, we're going to look at some rules for taking derivatives that will allow us to use shortcuts to find the derivative and will allow us to not use the longer method that we've been looking at over the last couple weeks, where we have to take the limit of a rational expression and simplify a lot of algebra. In this particular section, we are going to prove each of the differentiation rules that we're going to use for the rest of the semester. And so because there are proofs involved, this is going to be somewhat mathy, but then this will allow us to use these shortcut options as we go forward. The first differentiation rule we're going to consider is that of a constant function, like the one that's shown in the graph here. Just by looking at just by looking at this graph, we can see that the equation of any tangent line is also going to be a horizontal line, and we're expecting the slope of that line to be 0. But we want to prove that to ourselves mathematically. So let's make some space here. I think I can move this down. So let's consider a function that is just a constant some value c. The derivative of this function, using our longer definition, will be the limit as h approaches 0 of f of x plus that value h minus the original function divided by h. Now we can see by the picture above here, no matter what value we plug into the function, the output value is going to be c, right? We can see that our y value in both of these cases is c. So what we'll have here is c minus c. In both of these cases, we just get that constant as the output over h, or the limit of 0, right? We've got 0 over h, so we don't need to worry about plugging 0 in for h. We're going to take numbers that are closer and closer to 0, and overall we're just going to get 0 for our answer here. So this is the mathematical proof that what we're seeing in this graph is verified, that the derivative of any constant function is just going to be the number 0. So we'll use that when we're taking the derivative of a polynomial. Any constant that's on the end will just sort of be nominal. The next rule we're going to look at is the power rule. The power rule is one that I think a lot of you may know or remember from high school, where the shortcut version is that you can bring the power or the exponent down into the front as a multiplier and then drop the exponent down by 1. So when we look at an example over here in this picture, if we started with, let's say, the graph x squared, y equals x squared, the derivative of that, oops, I lost my slide here. The derivative of that would be 2x, bringing that 2 down into the front and then dropping the exponent down from a 2 to a 1. Show a proof of this power rule. We're going to use a fact that if we have x to the n power minus a to the n power, this can be factored into x minus a multiplied by, we're going to take x and drop the power down by 1. And then in the next term, the power gets dropped down again, but then we add a to the first power. Technically, I'm not writing it, but there's a to the 0 power here. And then we continue on this way. And then we'll have coming up with x to the first power, a to the n minus 2 power, and then a to the n minus 1 power. And similarly, we have technically x to the 0 power here, but we don't typically write it because anything raised to the 0 power is just 1. You can verify this fact by multiplying this whole thing out, which is kind of time consuming, or just seeing that if we were to do long division, taking x minus a and dividing it into the original polynomial, I'll put x to the n power out here first. And then we're going to have a bunch of blank, I'm going to leave blank space here and then put a minus a to the n out here. I'm just going to show you the pattern of what happens. I ask myself, what do I need to multiply this first term by to get this? And it would be x to the n minus first power, right? And then I multiply both terms by that x to the n minus first power. And I would write, when I multiply these two together, I'll get x to the n power. And then when I multiply these two together, I'll have minus a times x to the n minus 1 power. We subtract both of these items. So this is a minus, this changes to a plus. So then this term comes down, ax to the n minus first. And then I repeat the process. What do I need to multiply this by to get to this term? And that's going to be, we need an a, and then we need an x to the n minus 2. And then, oops. And then repeating the process, I'll take this guy and multiply by the first one to get ax to the n minus first power. Then I'll multiply this by the second one, and I'll have minus a squared x to the n minus 2, and so on. And then we follow the same process where we subtract, this changes to add, and then we bring this term down. You can see that each time what's happening is that the term of a is going up 1 in power, and the term of x is going 1 down in power. And if you add both of the exponents together at every stage, they add up to n minus 1, right? So again, we're going to use this fact when we're doing the proof of this. This is background information. Again, what we're trying to prove right now is the power rule that will allow us to much more easily take the derivative of polynomials. So now we're going to move on to the proof part. So we're going to just start with a simple function. We'll just take f of x to be x to the n power. And then the derivative at some particular point is going to be the limit as x approaches a. And then we'll take the original function minus the value at that point over x minus a. We're using two different definitions in this presentation. The first one, we were using the definition where h goes to 0. We're picking some point off in the distance from a particular point. In this example, I'm using two different points, x and a, on the graph, and just taking the slope between them, the slope of the secant line, and bringing those 2 points closer together. So when I plug x into the function, I'll get x to the n power. And when I plug a into the function, I get a to the n power. So this is where that first part is coming up. I'm taking x to the n minus a to the n, that was here, and I'm dividing it by x minus a, right? So that's why I had that long division at the front, so that we can use the fact that we had at the beginning to say that this is going to be this long polynomial where each of the x terms is going down by 1 exponent and the a terms are going up by 1. Okay. Now what we're going to do is everywhere that we have x, we're going to plug a in. We don't have any restrictions as far as fractions or places that we're going to have discontinuity. So when we're taking the limit here, we can just plug a in wherever we see x in the polynomial above. So we're going to end up getting a to the n minus 1 power plus, looking at the second term here, I have a to the n minus 1 and a to the first. So, or sorry, a to the n minus 2 and a to the first. So that also is going to become a to the n minus 1, and so on. Each of these terms, when we plug a in, we're going to get this. And we have n of these. So that is n times a to the n minus 1. And that proves our theorem. We started with something like a to the n power. We bring the power down into the front, shows up here, and then we take this value and we subtract 1 off the exponent. And that shows up here. As an example of how this will work, if f of x is x to the 5th power, the derivative will be 5x to the 4th. The 5 that's the exponent comes down into the front, and then we drop the power down by 1. If f of x is x to the 10th power, the derivative will be 10x to the 9th power. This is a really powerful theorem because it really simplifies the work that we're doing as we're taking derivatives. Mom, going back up to this original slide, we just proved this theorem here, the power rule. And the next one we'll look at is the derivative of a constant that is being multiplied by some function. So in this case, we're taking u to be a function, and we're taking c to be a constant. So I'll show a short proof for this. I think I'll go over here. So like taking the derivative, this is a different term way of writing it rather than f prime, the derivative with respect to x of some function u that's got c, a constant, multiplied in front of it. We'll use the h going to 0 definition for this one. And so this will be c times u of x plus h, and then c of times u of x. So I've got u of x is the function, and I've plugged in u of x plus h, and I've plugged in u of x, and both of them are being multiplied by that constant c in the front. And then we've got h down here. If I factor that constant c out to the front, then I have u of x plus h minus u of x. And we saw a couple weeks ago that when we had a function of a limit versus a limit of a function, we could pull certain aspects out. We did that specifically with some of our square roots, where we pulled the square root outside the limit. And so we're going to use that same property now and take the c and pull it out to the front. So we'll have this constant multiplied by the limit, like this. And then this part here that's in brackets is just the derivative of u of x, right? So that's just du dx, and that c is being multiplied down the front. So what this is telling us is that if we have a constant in front of a polynomial, it's kind of just hangs out there and you take the derivative of whatever's left. So as an example, kind of related to kind of combining these two ideas together, let's say that the example that we just did was x to the fifth, and we said that the derivative was 5x to the fourth. Well, what if we modified that? What if instead we had 3x to the fifth? The constant rule that we just used said that we can just kind of ignore this 3. It's going to just hang out there and stay as a multiplier in front. So when I take the derivative, I'll leave the 3 here, still bring the 5 down in the front, and drop the power down by 1. So I end up with 15x to the fourth. This next rule is taking two different functions and then adding them together, or we could subtract the functions. So we want to make sure that if we have two separate functions, we can take the derivative of each of those functions individually. So that's what this proof is going to be. So the two functions that we have are u of x and v of x. So our functions are u of x and v of x. And we want to take the derivative of the sum of these two. So if we look at this as a single function, we would first plug in x plus h, so u of x plus h plus v of x plus h. That's the first part. And then we would subtract off the original function, which was u of x, plus v of x. And that whole thing is divided by h. So looking at the first, if I sort of rearrange this and take this guy and put this guy together with it, so u of x plus h minus u of x. And then similarly with the other two, put them together. I'm going to take this guy and put them together. So I'll have a plus v of x plus h minus v of x. I'm taking that subtraction sign and distributing it to both items. So that's how I'm getting the subtraction there. Then we can see that by just taking this guy on its own, that is, actually, I'm going to split this into two fractions just so we can see it more clearly. So here's the first guy and then the second guy. So then the first one is the derivative of u, and then the second one is the derivative of v. I mean, technically, if we wanted to get technical about it, we should probably do that. I'm going to copy this whole thing and put it down here. And then I'm going to move this over. And then take this and put it here. I'm just kind of going like to be precise that we're breaking the limit into two things so that I can say, okay, this is, I didn't mean to change that to blue or red, sorry. I can say that this here is du dx, the derivative of the function u, and I can say that this part is the derivative of v with respect to x. And so that proves that if I take the derivative of the two functions individually, then I have the derivative of the polynomial overall. So as an example, if I have the function, let's say, f of x equals 3x to the fourth minus 5x squared, I can take the derivative of each of these individually and just subtract them. So I would get 3 multiplied by the 4 as the exponent comes down to the front, and then I subtract 1 off the exponent. So this is a 12x cubed. And then for the second one, the 5 stays where it is. I bring the 2 down and multiply it. And then I drop the exponent down by 1. So x to the first power. So this would be minus 10x. So this is going to allow us to just take the derivative of each term individually without having to go through all of this algebra with taking limits and everything. And then the last, oh, I think I had an example problem I wanted to do up here. Hang on. Yeah. Looking at this curve, it's the graph of x to the fourth power minus 2x squared plus 2. And we can see in the picture that there are some horizontal tangents, but how can we show mathematically where those horizontal tangents are? If we didn't know what the graph looks like, and the reason the horizontal tangents mean something to us is because we can see that they end up being relative max and relative min points. And so this is how we'll use the derivative to figure out something about the graph. So taking everything we've done so far, let's take the derivative of this function. So the derivative of the function y will be 4x to the third power, taking the exponent of 4, bringing it down into the front, and then dropping the exponent down by 1. For the second term, I've got a minus 2. It's going to be multiplied by that 2 as the exponent. So that'll be a minus 4x to the first power. And then the very first rule that we saw showed that the derivative of a constant is 0, so we don't have to write anything there. Now, the tangent line is going to be horizontal when it is equal to 0. Slope equaling 0 means it's a horizontal line. So we want to know, when does this function equal 0? If I factor this, factor a 4 and an x out, I'm getting that x is either equal to 0, 1, or negative 1. And I can see that those are the points on this graph where we do in fact have relative max and relative min points. So again, this is the application that we'll be using the derivative for. All right, our final rule for this part of the video is finding the derivative of the exponential function. So let's let the function be e to the x power. Then to find the derivative, let's take the limit as h approaches 0 of, so we'll plug in f of x plus h minus f of x over h. So I'll have e to the x plus h minus e to the x. And then when you have exponents that are added, that's the same as if you had the same base and it was multiplied. So e to the x times e to the h. I'm separating it, or I'm breaking it up like that because then I can factor e to the x out to the front. So I'll have e to the h minus 1. Okay. Now, e to the x is just a constant. It's a number. And we have shown that we can pull a number out into the front when we're taking a derivative. So I'm going to bring that e to the x out into the front and multiply it by this limit, like this. To just kind of simplify what we have. And then looking at what's inside the parentheses, if you plug in different values, and this is actually kind of a separate theorem, but we're just going to kind of wave our hands a little bit here. We can plug in different values of h that are very, very close to 0, and this is going to go to 1. Which is sort of weird because now what we're saying is the derivative of the original function we had is e to the x, that the derivative of the function doesn't depend on h. It doesn't matter how far away or close you are as getting close to a particular point on the graph. The derivative of the function is exactly the same function, which is probably the easiest derivative of all to remember. So let's do an example problem. I have a graph over here of e to the x, that's the blue line, and we want to find an equation for a line that is tangent to the graph and that crosses through the origin. So that's the red line that's drawn there is a picture. So we know that there are 2 points on the graph. One of the points is, or on the line, 0, 0. That's the point here. And then the other point on the graph is a e to the a power. For some value a, we don't know what this value is here, but this is going to be the other point. And so we'll use those 2 points to find the equation of the line. So we know that the slope of that particular line will be the y values, e to the a minus 0, over the x values, a minus 0. So e to the a over a. We also know that just looking at the graph, that in general, this equation is going to be something of the form y equals m times x. The plus b, the y-intercept is 0 because it's going through the origin, so we don't have to worry about this part. We know that that's the general format that this line is going to look like. And we just found that the slope is this. So we think that the equation is going to look something like y equals e to the a over a times x, right? All right. Now, that's kind of the first part. The second part is that what we just saw was that the derivative of e to the x is e to the x. This will be the slope of any tangent line. Well, we're looking at the slope of the tangent line specifically at the point A, aren't we? So in this case, we're going to say, all right, well, the slope of a tangent line at x equals a is going to be e to the a. Well, we just said the slope was this, and now we're saying the slope has to be this. So for these two to be equal to each other, a has to be equal to 1. So then that means that e to the a over a is just equal to e, because a is equal to 1. And so then the slope of our line, rather than being this, here, this for a sec, our line we think is going to be y equals e to the a, or sorry, e times x. So we're saying that that is the equation of this particular line. All right, we've covered a lot of proofs in this video, but in class, we will go over example problems, and you will probably be very happy to find that the problems in this particular section are much easier than what we've been doing. Thanks for watching, and I'll see you in class.